Welcome to a VIAVI webinar. Today's session is about data-intensive application and design consideration for PCI-express. Good morning again. I'm Giulio Spinelli, based in Italy, Milano, and I cover the role of European BDM and solution specialist for VIAVI CST product line portfolio. I'm coming from different roles at technical and management level. And today, which topics are we going to touch? Let's have a quick look. So after a quick intro about VIAVI, for the ones who don't know the brand, I will share some consideration about megatrends and their impact on application. We'll see new challenges for developers or integrators and new opportunity for business. PCI is a key topic in these trends. I'll recap some characteristics of the standard, and then I'll present some design approaches and difficulties in validation and verification, and how VIAVI's gig suite can be used to overtake some tasks that can be difficult with the traditional lab setup. This combination can reduce time to market and mitigate the risk in validation, verification, and certification of hardware and software. Now, let's move on with the session. Few words about VIAVI Solution. VIAVI is over a $1 billion per year company, quoted at Nasdaq. Close to 4,000 people in the world with main R&D centers in Europe and North America. More than 100 years in the market, grown with acquisition and organic development. VIAVI has a leader position in the area of test and measurement and optical technology. And as I said, VIAVI is really a galaxy of products, so see how dense is this chart. For today, we will focus on what lab and production business unit can provide thanks to the computer storage and transport, CST, product line. So now you have a map if you want to look more for VIAVI. So what is happening? Mega trends are really fueling the growth of data-intensive application, resource virtualization, and dedicated processing unit. We see this in wireless connectivity, AI, ML application, in augmented reality, virtual reality, video services, social media, not to speak about smart application, smart cities, IoT, automotive, military defense, aerospace, and avionics. This means that we have emerging challenges in computing, in storage, in energy, and in connectivity. PCI-express is the backbone of the new growth, as you can see from this slide. The widespread of PCI-express as a connectivity solution has extended beyond servers and personal computer due to the performances and cost effectiveness for data-centric application. PCI-express standard is continuously evolving with specification that double the input-output bandwidth every 3 years. These allow to keep up with the growing demands of high bandwidth, low latency, and energy efficiency. Business side, PCI-SIG, that is the standard for PCI-express, is expecting a compound annual growth rate of 14% by 2027. Just to give you more an idea of the standards around PCI-express, PCI-SIG is the organization that is evolving PCI-express specification. And PCI-SIG just celebrated 20 years of PCI-express specification. In over the past 20 years and 6th generation, the PCI-express, PCIe, specification has been the industry high-speed I/O interconnect of choice for application ranging from personal computer to advanced AI platform. First introduced in 2003, PCI-express architecture uniquely meets the industry need for a system interconnect with greater bandwidth, scalability, and lower cost of implementation. Just to give you an idea, the latest version, the PCI-express generation 6.2, provide nearly a terabit per second via by 16 configuration. So now, why PCI-express? PCI-express is a connecting technology that allows optimized exchange of data inside the system. This, by design, allows superior performances, thinking to latency, forwarding efficiency, or data coherency. From the old days of PCI, that was a parallel bus, to interconnect just IOs, became serious, and PCI-express in the early years 2000, in 2002, became serious, replacing internal buses. And storage with NVMe and processing unit with the CXL as alternate protocols are relying on the performances and robustness provided by PCI-express. So what is PCI-express then? PCI-express is a high-speed serial computer expansion bus. Is a point-to-point connection with independent bidirectional communication. We can recognize root complex and endpoint in this communication. Root complex is usually hosted inside the main CPU in the switching context. And it is possible to aggregate several endpoints with the switches. One good thing is also that endpoint-to-endpoint communication is possible without having RC, so root complex, in the middle. PCI specification said are evolving generation after generation, from generation 1 to generation 7 expected by 2025. The changes go beyond the speed capability, and as an example include error connection nodes and other updates. So we can say that PCI-express is future-proof and also past-proof, considering the compatibility required through the different generation. So we said that PCI-express is a point-to-point connection. This connection is referred as a link. A link may contain several lanes. When you see X1, X2, by 4, by 8, by 16, this is the number of lanes concurrent to create the link. So when you see X is pronounced as a by. A lane is composed mainly by two differential signaling pairs, with one pair for receiving data and the other for transmitting. So each lane is composed by 4 wires or PCB traces. So we could think each lane used as a full duplex bit stream, transporting data packets in 8-bit byte format simultaneously in both directions between the endpoints of a link. PCI-SIG describe the architecture in terms of 3 discrete logical layers: the transaction layer, the data link layer, and the physical layer. Each of these layers are divided into 2 sections. One that process the outbound to be transmitted information, and one that is that process the inbound received information. So PCI-express use a packet to communicate information between components. Packets are formed in the transaction and data link layers to carry the information from the transmitting component to the receiving component. And as the transmitted packets flow through the other layers, they are extended with additional information necessary to handle packets in those layers. Note that a simpler form of packet communication is supported between 2 data link layers that are connected to the same links. And this is for the purpose of the link management between the 2. So starting from the transaction layer, The upper layer of the architecture, as said, is the transaction layer. This layer is connected to the application with operating system drivers. The transaction layer's primary responsibility is the assembly and disassembly of transaction layer packets. So it's quite obvious. Transaction layer packets are used to communicate transactions such as read and write, as well as certain types of events. The transaction layer supports 4 address spaces, so memory, I/O, configuration, and message spaces. Here, one thing interesting to see is that the message space support all the former PCIe physical sideband signals. So moving from parallel to signal, this has been introduced, and we could think of PCI-express message transaction as virtual wires, since their effect is to eliminate the wider rate of sideband signals used in a platform implementation. Each packet has a unique identifier that enable a response packet to be directed to the correct originator. Every request packet requiring a response packet is implemented in a split transaction. Think to a memory read as an example, where you have a request and then you are looking for a response. Right below the transaction layer, we have the data link layer. The primary responsibility of the data link layer include link management and data integrity, including error detection and error correction. The transmission side of the data link layer has set the TLPs assembled by the transaction layer here above, calculates and apply the data protection code and a TLP sequence number, and then submits them to physical layer for transmission across the link. On the other side, the receiving data link layer is responsible for checking the integrity of receiver TLPs and for submitting them to the upper transaction layer for further processing. On detection of error-read TLPs, data link layer is responsible for requesting retransmission of TLPs until information is correctly received, or the link is determined to have failed. Data link layer also generates and consumes packets that are used for link management function. So the data link layer packets, DLLP. And DLLP is always intended for the device on the other side of the link. So if you see the picture, DLLP are really on the two sides and TLP is end-to-end. The data link layer tracks the state of the link and communicate this status with both the transaction layer and the physical layer through a state machine. And I put in the slide just for remember this point. Down one layer more, we are at the physical layer. This layer is responsible for converting information received from the data link layer to appropriate serialized format and transmitting it across the PCI-express link at the frequency and with compatible with the device connected on the other side of the link. The physical layer is divided in the logical and the electrical subblock, as you can see on the screen. Some function of the logical subblock are the link training, the data scrambling, the scrambling, data encoding, decoding, packet framing, the framing. When we think to the electrical subblocks, we have serial parallel and parallel to serial conversion, some clock extraction, some lane-to-lane DSQ, the differential signaling, PLL timing circuit, emphasis of or the emphasis of the let's say output and input stage. It is not all here. There is much more in PCI-express specification, and just trying to summarize, and perhaps we can reserve other webinars. We have the link training and state-to-state machine that the state of a link is defined by this state machine. So from an initial state, the state machine goes through various and different measure states like detect, polling, configuration, to train and configure the link before being fully in a link up state that is named L0. Another thing we cannot forget is the configuration space. The configuration space provide a standardized and flexible way for the system software to discover, configure, and manage devices connected to the PCI-express bus. This simplified the process, improve compatibility, and allow for efficient utilization of various features offered by different designs. So you don't need to plug any more jumpers on your board. Gen 6 is coming, and with the generation 6, the packets move to fleet mode and PAM4 modulation. Fleet mode is a new concept introduced in PCI-express to improve efficiency and performance. We have fixed size packets that allows higher bandwidth and throughput and lower latency. And it is crucial in real-time operation and also allow to simplify the controller. Why beneficial? Fleet mode presents also some design and verification challenges for the hardware and software developers. Signaling with PAM4 modulation introduced to double the bandwidth is leading to a trade-off around errors, correlation, channels, performances versus area, and circuit complexity. So on one side, we are pushing the performance in, on the other side, we need to set some more implementation challenge. Another thing that PCI-express is taking care is trying to go low power. So on top of existing methods like 0S, L1, dynamic width, or speed change, a new low power state at 0P has been introduced with Gen 6 to have power consumption proportionated to the bandwidth usage in that moment without impacting traffic flow. So you really size your need of lanes depending on the bandwidth you're transferring. So as you can see, for this quick intro to the specs and possibilities, there is quite a lot to consider during design testing and integration activities. And so why a protocol analyzer suite? We are seeing mega trends are pushing the performances. We are seeing now PCI-express can support these performances, and of course it's back compatible, future-proof, but it is requiring new way to during validation and verification. Also, interoperability with other devices could present difficulties, as well as ensuring compliance with industry regulation and standards. These challenges can be addressed thanks to instruments that help in testing and incorporate a full understanding of the PCI-express technology and its evolving specification. Here a quick tour about what we have in the lab typically. And if we think to a lab instrumentation set, we typically have the oscilloscope for sure, for the first integration of signal integrity status of the board. That is a very useful tool to have. If we are more in the physical area validation, for sure a bit error rate tester is an option to measure error rate and in case we want to really test the electrical side of the physical layer with just agnostic patterns without going in the aim of the protocol. Then we could have analyzers, a tool that provides a deep packet inspection to the bits on the wires and comprehensive analysis of every protocol layer in the stack. On top of analyzer, exerciser connected as an end device to simulate the stress condition, test compliance, and performance of a component. We could also add a jammer if we want to create inline errors to test the capability, the recovery capability of our availability suite or the system itself. So if we want to test the robustness of our system. So as you can see here, a different view of the former slide that help us to understand how we can cover the different layers of the PCI-express connection. And as you can see, oscilloscope can cope for sure with the low level of the stack, but then you need to move to analyzer, exerciser, and jammer to improve a lot the level of coverage you can provide. Just a couple of pictures to show how different tools are capturing and injecting data from the system test. So you can see from on the left, the analyzer is between a link between the endpoint and the root complex, and we spill the traffic through the top port. With the exerciser, we can replace one of the two sites and behave as a golden, proven by specs counterpart. A jammer can replace some bits and bytes of the packets that are going back and forth to check the robustness of the system. Here is a different view, more let's say with picture that show in practice the way it works. So in VIAVI, we have a main chassis where the major part of the VIAVI software is running. Interposer, the probe for the signals, and a, let's say a PC, a laptop with a GUI running that can also be remote. It is, I think it's worthwhile to consider also some stories from the lab and to show that with supporting customer, you know, I've collected some of the common pain points. These are just a few in the slide, and these are being addressed and solved using PCI using VIAVI ISGig PCI-express platform. As you can see, some of them are due to signal integrity, but only with the analyzer, customer managed to find the real root cause. As an example, expected link width not achieved was due to a poor signal integrity and wrong equalization parameters. Last week, I had another use case where a customer couldn't reach the required speed and was not capable to capture the reason. And thanks to the protocol analyzer and the capability from the protocol analyzer over a specific transition of the link to trigger the oscilloscope, was possible to intercept the signal integrity issue again. So as you can see, the protocol analyzer can help a lot in debugging and verifying the system. But once the device under test is working in the lab, how to be sure that will work with other parts of the PCI-express ecosystem. To assure interworking through parts of different vendors, PCI-SIG has a specification for compliant testing. Compliant testing is split out in two main sections: the protocol compliant testing and physical layer testing. On the protocol compliant testing, you check protocol specification, timing test on protocol level, link training, lane margining. These are verified during the protocol compliant testing. Instead, something like height diagrams, mask test, physical layer timing, jitter, line reflection, clock timing, these are indeed part of the physical layer testing. So the compliance test is typically part of the software suite of an exerciser. This is an example of the specs PCI-SIG provide in order to go through the compliant testing test. And just to show something that implement these things, the VIAVI XGig 5P16 exerciser is a PCI-SIG approved as a Gen 5 and Gen 4 link and transaction protocol compliant testing. For your information, PCI-SIG has not yet released the final version of Gen 6 compliant testing, but we are working with the standard using the draft specification. For the one of you that are interested in CXL, I think it's worthwhile also to mention that CXL Consortium has a similar approach for compliant testing, and XGig 5P16 exerciser is also an approved CXL 1.1 Gold Suite solution. We are moving now to the tools that VIAVI can provide you in order to make your life easy in the lab. So we have seen so far how PCI-express can fit the needs of that intensive application, how many different aspects we have to consider during the development, verification, integration. And the VIAVI XGig portfolio is a powerful and versatile PCI-express testing solution. Chassis and software key licenses allow you a pay-as-you-need approach, enabling the feature you want when you need. We have multiple functions in a single platform, so you can achieve equipment optimization and reduce the total cost of ownership. As an example, analyzer, exerciser, and jammer are supported by the same chassis. On top of it, we have a robust software tool suite for all XGig platform with post-capture analysis. We will spend some words later. We spoke about chassis. Here are a couple of pictures about them. And when we think to interposers, as you can see, there are different flavor of them to allow you to interconnect different part of your system. And the typical starting point here are the 16 lane CAM interposer or the ETS, the host test stand. These are the two that for the most are helping customer in starting the analysis with their hardware. We spoke about Gen 6 and Generation 6 for Generation 6 is already available, an exerciser, and soon we will release the analyzer. We are already working with the selected customer with these products. I think that it is not only the hardware, but is really worthwhile to mention the software suite available. Because on top of the modern GUI interface to configure and control the chassis, a very powerful viewer like TraceView is available, and a series of post-capture analysis tools are very, very appreciated by actual customer. These tools allow to view the captured trace from different corners, allowing a faster understanding of the performances and issues of the link under test. As you can see, you can see the data, let's say, bottom up with the LTSSM viewer, if you are interested more in the link up and link training part, or with the XGig expert as an example, it's more dedicated to the transaction layer analysis. We are nearly at the end of this session. we have seen how PCI-express as standard can support data-intensive application that nowadays megatrends are pushing, and how the classical instrumentation in the lab needs to be upgraded with the protocol-capable suite. In a lab, a protocol analyzer suite can be considered a versatile set of tools and can be used in a variety of ways, improving the performances of a system, addressing the compliant test of the implementation. Some common uses are in the IC components and board developments or system validation, or to improve the performance of software application and during the debugging of system drivers. In summary, the use of a protocol analyzer can help to streamline the process, leading to a faster time to market and to a reliable system. With that said, thank you for attending this session.